Okay,
Okay,
going.
keep going.
Now we
Now
study
we study lecture 2, part 3. Uh,
we
we discuss
the motion
motion
in the
in
two
2
and
and
three
3
dimensions.
dimensions.
Okay.
Okay. So
So
we
for the
have
learning
learning
outcomes of
outcomes
this
of
lecture.
these lectures.
Okay.
Okay.
So when we
So when we
finish this
finish
lecture,
these
you
lectures,
can
you can
understand how
understand how
to
to
represent the
represent the
position
position
of a
of a
body
body
in the
in the
two or
2 or
three
3
dimensions
dimensions
using
using
vectors.
vectors.
Okay.
Okay.
Determine the
Determine
vector
the vector
velocity
velocity
and the vector
and the vector
acceleration
acceleration
of
of
the body.
body.
Okay.
Okay.
Yeah.
Yeah.
So
So
it's
it's
a list
a
of
list
content
of content
for lecture
for lecture
3,
3,
lecture 2,
lecture
part
2,
3.
part 3.
Okay.
Okay.
Yeah.
Yeah. We
We discuss
discussed
two-dimensional
two-dimensional
motion.
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 Okay.
Okay.
Projectile
Projectile
motion.
motion. A
Particle
particle
in
in
uniform
uniform
circular motion.
circular motion.
Okay. This
Okay.
one is
This one is
very
very
important.
important.
Tangential
Tangential
and
and
radial
radial
acceleration.
acceleration.
And this
And
one
this
may
one
be
may be
for
for your
reference.
reference. Okay.
Yeah, relative
Relative
velocity.
velocity and relative acceleration.
Okay,
Okay,
this is a
so this is the
list of
list of
content
contents
of it
of it
two, part
2,
three,
part
and we
3, and
hope
we
we
hope
can
we can
finish.
finish the lectures next week.
Yeah.
Yeah,
We
so
can
we
review
review
a little
a
bit
little bit okay,
about
about
two-dimensional
two-dimensional
space,
space or
three-dimensional.
three-dimensional space.
Okay, so
Okay, so
any
any
vectors, for
vectors,
example,
for
here is
example, here is
vector
vector
vx,
vx,
we can
we
get
can get
vectors,
vectors,
for example,
for
sorry,
example,
vector
sorry, this is
v.
vector v.
So we
So
can
we can
analyze vector
analyze
v
vector
to
v to
become
becomes
vector vx
vector vx
and vector
and vector
vy.
vy.
Okay, that
Okay,
means
that
we
means we
consider
consider
reference
reference
coordinates
coordinates,
axis and
x-axis
y
and
axis.
y-axis.
Okay.
Okay, yeah.
We also
We also
discussed about
discuss
solid
about falling
objects, right?
objects, right? Yeah.
But this
But
one
this
is
one
only
is
one
only one
direction.
direction.
That means
That means
straight
straight
upward or
upward or
straight
straight
downward.
downward. Yeah.
It
It
depends
depends
on the
on the
direction of
direction of
velocity and
velocity
the
and the direction of
acceleration.
acceleration.
Okay, we
Okay,
can
we
know the
can know
speed.
the speed.
That is
That is
increasing or
increasing or
decreasing, right?
decreasing, right?
So this
So
one
this
here,
one
the
here,
speed
the
is
speed is
decreasing.
decreasing.
Now
Now
the speed
the
is
speed is
increasing.
increasing.
Okay,
Okay,
right.
right? Yeah.
Multiple choice
Multiple choice
questions.
questions. Okay.
Look the
Look, the
pole.
pose
Take
take
2 seconds
2 seconds
to reach
to reach
its
its
highest point.
highest point.
So
So
approximately how
approximately how
fast was
fast
the
was the
pole
pole
moving
moving
when it's
when
left
it's left
the
the
player
player
foot?
foot?
Okay,
Okay,
and
and
yeah, you
yeah, you
just
just
use the
use
formula
the
to
formula to
calculate very
calculate
quick.
very quick.
Okay,
Okay,
now
now
fill in the
fill
gap,
in the gap,
right?
right?
Okay,
Okay,
blah blah
of
blah
blah blah
of
blah
the
of
vector
the
is
vector is
always a
always a
positive
positive
quantity.
quantity.
Okay,
Okay,
positive
positive
quantity. So we
quantity. So
have
we have
amplitude, right?
amplitude,
And we
right?
have
And we have
magnitude,
magnitude,
right?
right?
For
For
amplitude, we have
amplitude, we have
positive and
positive and
negative.
negative.
Like
Current,
we have
we
current
have
A
current is
I
I
sine
psi
omega t.
omega t.
Omega.
Omega
So
t.
this
So
one
this
is
one is
amplitude.
amplitude.
Okay, for
Okay,
example,
for
you
example, here
get
you get
phi
phi
sine
sine
omega t.
omega t.
So
So
here you
here
can
you
get
can get
amplitude, right?
amplitude, right?
Yeah,
Yeah,
like this.
like this.
Yeah.
Yeah.
Omega.
Oh my God.
Okay.
Okay,
That's good.
not good.
Okay,
so this one is 5m dash,
and this one
and this one is minus 5m dash. Okay,
so
so the answer is magnitude, of course, because
magnitude
magnitude is always positive.
okay.
Okay,
Sometimes
sometimes we can say it's absolute value.
okay.
Okay,
Now
now very easy, right? Ax is positive
if
if Ax is directed
y
y-axis, right?
yeah,
Yeah, so that's mean
right
right side,
and
and this one means
upside,
upside, right?
Yeah,
Yeah, right side and upside, right?
very easy.
Very easy.
Okay,
Okay, just review. Okay,
before
before
we
we consider two or three
dimension
dimensions of
the
the
moving
moving objects. Okay. Okay. The acceleration of a cart rolling down a ramp. We have a ramp. Okay. Alright. And this is the round, right? This is the round. And we have a cart here. Okay. Yeah, rolling down. Okay. Okay. C, AB. Okay. Yeah. The answer is the angle of the ramp. Okay. The angle. You need to explain for yourself. It's very easy. So we don't have more times. Okay, continue. The acceleration vectors of particles in the projectile motion. Just think about it because we haven't studied projectile motion. Okay, just rethink about the answers. Okay, and later on, so, okay, when you study projectile motion, okay, we come back and you can understand more. Okay, projectile motion like this, right?
Yeah.
Yeah. Right. So this is final position. This is initial position. This is final position. Okay. So the acceleration vector is directed down at on times, right? Okay. And yeah, we have some rethinking questions. Okay. Now, if we use the vectors, we can explain the questions before. Okay. Yeah, of course, every vectors we have magnitude, and the direction of the vectors. Okay. Yeah. So remember that when we have the direction and we have x, y coordinate, we have four quadrant, right? The first quadrant, the second quadrant, the third one, and the last one, four quadrant. Okay. So when we consider what kind of quadrant we have, now which is and then the magnitude is always positive. Okay. This one like complex number, right? We have the z is a plus jb, and this is magnitude or the absolute value of z. Okay. Yeah. Okay, very easy. Okay. And we also study vector addition, right? So any vectors we can get some components, right? We have x-axis component and y-axis component. You take addition, you can get the c, right? Okay. Yeah. So the given vectors b and vector q, what is b plus q? Okay. So this is b, this one is q, right? Yeah. So when we apply the theory, you can get the SSA, of course. Okay. Yeah, we have multiplication of boundary by a scalar. Yeah, we studied before to just review. Okay. Yeah. This is A plus B. Now for to subtract B from A. Okay. B from A. And we firstly draw vector A, and then plate the tail, right? Plate the tail of minus B, blah blah. Okay, so yeah, anyway, we studied before, so just give it. Okay, this is vector B, this is vector Q. Yeah, so you can get the relative vectors will be like this. Okay, so the correct answer is question D. Yeah, answer D. Okay, yeah. Coordinate systems. Yeah, remember that we have reference axis, x-axis, and y-axis. Okay, so any vector A, we can get x-axis component ax and ay. Okay, yeah, this one for two dimension. Okay. Yeah, and so we mentioned before, we have the magnitude is always positive, or we can say we have the absolute values of ax. Okay. So just mention about that vector a's, you can get vector ax plus vector ay. Okay. So if we say ax, so we should use unit vectors I overhead and ay j overhead. Okay. So for the final exam, some students write it like this. Okay, it's wrong. It's wrong. Okay, you should use vectors. Okay, otherwise it's wrong. Okay, remember that. So we have two representations. This is the combination of vectors components, or we can use unit vectors. Okay. Do you know unit vectors? Yes. Okay. Yeah. So this one for the first current. So this one for the second current, right? So we have bx and by. So here, if we say vector b is vector bx plus vector by, right? We don't know which current we have. We don't know, right? Because this one just vector, this one just vector. But if we know minus bx I overhead plus by j overhead, I know this is the second one, right? Okay. So if you just analyze vector b to become two components, bx and by, we don't know which current we have. But if we use this format, I know, okay, vector b's belong to the second current. Okay? Yeah. Or we can apply the theories of complex number. Okay? We can get the magnitude and the phase angle. Okay? We also calculate the ix. Okay? The absolute value ix and y. Okay? Yeah. Very easy. Yeah. Just review. Okay. We have this vector, so you can guess a acted the vector a, so you get ax is 2 and ay is 3. Okay. Yeah. And this is the last current, four current. Four current. Okay, so this you get minus 4 and 3. Okay. Yeah. Some cases we have the health of the vectors is places at the origins. But for some cases here, but that's okay. You can move or you can translate the tail for the vector to be here. That's okay. Otherwise, you just consider here, and then you can guess cx, and then you also get cy. Okay? Yeah, it's up to you. Okay. Yeah. So we can guess cx is minus 4 and cy is 2, right? Yeah. Why? Because sometimes we have many vectors. We have many vectors. And then we only have one coordinate system. Okay? Any physical model, we only have one reference axis. Okay? In the same question, we cannot choose more than one reference axis. Okay? So you have many vectors. Okay? So we need to translate the vectors come to the origin. Okay? For example, I give you the circuit, you get resistance. Maybe I use black white. Okay. Here, for example, we have R1, we have C1. Okay. And then here we have what is V1. Okay. This is vectors. Okay. And then we have current I1. Right? This circuit we say is AC circuit. Okay. Yeah. Look. This one is AC signal, right? So AC signal. That means we can analyze what is AC voltage. So we can get V1. If this is the function of time, so V1 is V1, right? Capital V1. So I assume this is sine omega t plus 0. Okay? So that means we have a waveform like this. This is V1 times this is sine omega t, right? And this is 0, so you start from origin, right? Okay, because this is omega t. Omega t is 0, sine 0 is 0. And then if omega t is pi over 2, you get max is now V1. Okay, and this is pi, this is 3 pi over 2, you get minus V1. Okay, so you get the curve like this. You with me? Okay, so if I use reference axis, this is x-axis. This one is y-axis. Okay, you get vector V1. You get vector V1 should be here. Do you read me? Because this is 0, so now we have V1 vector V1 is magnitude of V1 and 0 degree. Okay. So now we have this vector. So here I1 is also the vector. Okay. And if we consider here, what is it? This one is VR. It's R. Okay. And this one is VC. Right? This is the vector. This is the vector. And then we only have the same coordinate system. You need to indicate 4 vectors in the same coordinate system like this. Okay. Like this, I showed you before. Right? So how can we do? Very easy. Okay. Very easy. So now we analyze our what? We know VR1 is I1 R1. Okay. This one like scalar number. That's right? And I1 is vectors. We don't know I1. So we cannot draw VR1. Yes, of course. Okay. So we need to consider VC1. VC1. Okay. So VC1 is what? is what? ECE, right? ECE times I1. Do you read with me? Yeah. Okay. ECE. So ECE is what? ECE is 1 over J omega C. Omega C, right? Okay. Yes. Okay. So we need to make clear what's the difference between XCs and ZC. Okay, very important. Okay. When we consider ZC, this is the vectors. This is the vector. Okay. Or we can say we get minus J1 over omega C. This is XCs. Okay. Yeah. Don't worry, we study electric circuits. Or maybe this one you study from high school, right? No. Not yet in high school. No. Really? You only know of XC, okay? Reactants. The best reactants. Okay. Sure. Why? Maybe in high school so now we can get impedance total, right? Impedance. So now this one is R1, so R1 we get units here, and we have axis is the units is also ohm, right? So now we can get R1 minus JXC. You read me? Right? This one plus this one. Yeah. That means you can get this one. Okay. So if you use XC dot, oh my God, you are really stupid. Right? Very stupid. Don't do this one. Okay. XC just divide by this ratio. You know? Yeah, this is scalar number. Okay, so what is the key difference? Yeah, this is the key difference between XCs and ZCs. This is complex number. Okay, and XCs is scalar number. Okay? Yeah. Very easy, okay? So because this is scalar number, so now we can get complex number. Okay? So now I say we have V1. So V1 now is I1 times R1 minus JXC. Do you read me? We apply good job. Do you know good job? Yes. Oh, good. Okay. Now you can get I1 times R1. You know? Of course we have I1 is I1 sine omega t plus phi I. Okay, we have phase angle. Yeah. Or you can say we have vector I1 or I1 co-product is complex number. Mean you get the magnitude of the phase angle. Okay. Trying to make familiar with it. So now you get minus J I1. Okay. Axis. Okay. We don't know phi 1. We don't know. But you can calculate phi 1. If we know R1 how many? Okay. For example, we get R1 is 5 ohm, and you get CC maybe 10 microfarad. Okay. These are values. Then you can get. And we know this one. Yeah. We know this one. So you can get I1. Right? Understand? We also get the magnitude of I1 and the phase angle. Okay. Now this one. So now we have vector V1 these vectors minus these vectors. Okay. And now for example here I just assume here is I1. Just assume. I don't know. Because if we know the values, we can get exactly what is the magnitude of I1 in the phase angle. I don't know. I just assume C is I1. Okay. So we can get vector VR1. Okay. You can get this is I1 R1. You read me? Because this is scalar. This is scalar. Scalar kind of vectors will be in parallel with I1, right? Okay. Look. This one is minus. Okay. So if minus, so here. How can I say minus? So if here is I1, so minus, that means this one. Minus. Okay, this one is J, so this one is a minus J. Right? So you can get the vectors here, here. How can I talk here? You can get because we know V1, right? You know V1. So now we have V1 minus what? Minus I1. Okay. Minus I1 R1 is minus J I1 X6. Okay. So now we have V1 and minus this one, right? Minus. So minus should be here. Okay. Right. And you know this is minus. So now like this. Right. And then this one is minus J X1. I1 X6. Okay. Yeah. Right. So this one plus this one is this one. With addition, right? Or this one minus this one is this one. This one minus this one. So now I try to use the same references and I indicate all vectors of this circuit. Okay. But now this one is very easy, because we only have two discrete components. This one and this one. But if we have more complicated circuits, we have more vectors. And just apply vector addition, vector subtraction, vector multiplication. You can indicate all vectors in the same coordinates. Do you understand? Okay. So some ones are really smart and they don't want to use V1 to be similar with XS. They don't want to do that. They try to use I1 to be similar with XS. That's okay. That means we move on vectors with the phase angle phi I. Okay. You rotate all vectors with the phase angle phi I. You get I1 to be similar with XS. That's okay. Okay, it depends on you. Okay, try to make familiar with this because you are electrical engineers in the future. Okay. So if you cannot draw the vectors, oh my God, don't do it. Okay. Yeah. Do you understand? Good. Okay. So, for example, we have more complicated circuits. Maybe it's like this. Okay. Maybe we have the circuits like this. Now we have. Okay. Like this. Yeah. This is V. This one is I, R, L, C. Okay, something like this. Okay, so we need to apply some theory to analyze this. Here we have IL. Here we have IC, right? Here we say maybe I1. So at the beginning, we think about V to be similar with x-axis.
Why?
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 Because the voltage here is normally constant.
The
The voltage is constant. For example, the voltage here 224 always. You know. So if we use the voltage, we have some advantage because we know the magnitude of the voltage is constant. But I want this is variable, not constant. Depend on how many what's the value C1, you know. That is the reasons. Normally we use the voltage like reference also. Don't use current. Okay? Because current is changeable. You understand? And the next semester you study electric circuit. Okay. Yeah. And some lecturers will for this use. Okay. So continue. Yeah. We also calculate the phase angle, right? The phase angle. Okay. Yeah. Okay. So this one is XY coordinates. Okay, and we always choose the reference axis like this, right? X-axis. Okay. So if you stay here, you can get the phase angles like this. The phase angle like this. You know, we follow counterclockwise direction. Okay. Yeah. We seldom use this phase angle. But you need to use this phase angle to calculate this one. Okay. Yeah. Why? Because as mentioned before, you know, we always choose x-axis like reference. So we always stay here. Okay. And then you see different phase for different vectors. Okay. We cannot stay everywhere. Okay. Yeah, you stay here and then you look at the phase angle. You can make the comparison. So if you stay anywhere, how can you do comparisons? You know. So if we have another vectors here, right? Here. So you can guess the phase angle will be like this. Okay. You stay here, you get the phase angle. Okay. And then you know, for example, here the vector A, here the vector C. So we know vector C is faster than vector A or leading vector A, right? Because you stay here. You stay here and then you can see C goes first. A goes follow C. Do you understand? Yeah. Understand? Yeah. Okay. So remember that. So if you are very familiar with the vector, you can stay anywhere. Okay, but you need to unify, you know, the same place when we analyze all vectors. Okay. Any questions so far? Okay, good. So very easy, you know. So if we would like to calculate this phase angle, very easy. So here we can guess that this one is CY, right? And this one is CX. Okay. Yeah. So when we calculate this, you know, only this phase angle we have tan phi CX minus CY. Yeah, why? Because we only consider this phase angle, so you take the absolute value. Okay, absolute value of CX divided by absolute value of CY. You can get phi, and then you calculate tan to the power of 1. You can get phi, right? Yeah, very easy. Okay, and very easy. So just give it, skip, skip, skip. Okay, skip. Now this one. Okay. Now we consider this object. This is a car, right? And the moving directions is not. I mean the moving direction, right? Moving direction. So we have this one is vector v. Yeah, and we need to choose reference axis, and the origins at the starting point. Okay, at the starting point. So you can get here is vector vx, and here is vector vy. Yeah, and we can know for the phase angle. Okay, yeah. And this is the initial position. This is the final position. Okay. Yeah. So if we know some certain parameters, we can calculate the others. Okay. Yeah. Now we consider this one. Yeah. We have a great, great. Slide down. A frictionless. Okay. Frictionless means this surface has no friction force. Okay, no friction. We have many kind of friction we will study it later. We have static friction. We have dynamic friction. And I also give you a hint. Okay, so you can predict the moving direction, right? The moving direction will be like this. I mean moving direction. Yeah, and then we choose acceleration will be the same with moving directions. With moving directions. Why? Why? Why we do that? Why we choose vector A to be similar with the moving direction? Because we can choose the coordinate like this. This one the x, this one the y. Right? So if you choose this one the x, this one the y, it's easy for you to get the analysis. Of course, you can choose this one the x, this one is y. No problem. But now, if here we have vector A, we need to analyze. We have vector AY and vector AX and AY. Why we do that? Okay, you think about similar. Okay, so if I say this one is vector A, this one is vector X, vector Y, so we only have A is AX. Right? I can delete AY. I don't have AY if we choose the coordinate system like this. Okay. But if you are really smart, okay, you can choose any coordinates you want. But remember, we have the time limit for the final exam. Okay. Yeah. Do you understand? Do you get my point? Female students? No? Guy? Any questions? And of course, this one, this space is increasing because vector A is the same direction with vector V. Okay. Yeah. Like I mentioned before, this is the moving direction, right? The moving direction. Yeah. If this is the moving direction of the object, you can get A, or they say AX, that's okay, because vector A similar to AX. Okay, so please use coordinate systems like this, like this. You can't skip some parameters. Okay, and your calculation will be similar. Okay. Yeah, and of course this one is gravitational force. Okay, gravitational force. So for gravitational force, we have x-axis and y-axis. Okay. So multiple choice questions. A pulse grows up direct. Okay, we know. So this one is moving direction. Okay, yeah. So so we can choose this one is x, and this one is y. Then back down. Which is the correct acceleration graph? Okay, graph. Okay, this is answers. Okay, we have acceleration. Okay, this is D. Okay. Later on we study and then you can understand more. Okay. So now just give it. Okay. Very easy. Okay. Now we go to the first session. Now we go to the theory. We have the position, velocity, and acceleration vectors. Yeah. And remember now we have coordinate systems. Okay, with x-axis and y-axis. Okay. Yeah. Displacement vectors. Okay. RF minus RI. RF minus RI, you can get delta R. Okay. So if we analyze RF is RFX plus RFY, and we have RI, we have RIX plus RIY. Okay. Yeah. So you can get delta R with delta RX plus delta RY. Okay. Right? So delta Rx is RFX minus RYX. Right? And delta Ry is RFY minus RY. RIY. Okay? Yeah. RIY. Okay? Or you can think about this one. We have delta RE, RF with the phase angle phi f minus RY with the phase angle phi I. I with the phase angle phi. Right? Because remember now we have two-dimensional space x, y. You stay here. So you get this one is phi f, this one is phi I. Okay? Yeah. Any questions so far? Any questions? Okay. And we have average velocities, right? Average velocity is defined by this displacement over time. Okay, we studied before, right? We have average velocity. Okay. It's here. It's this one. Okay. Average velocity. We have instantaneous velocities. This is the first derivative of displacement with respect to times. Okay, but remember that now we consider two dimensions x, y. Okay, yeah. So this one is instantaneous velocity. So instantaneous velocity is the tangent line of position curve, right? Tangent line. Okay. We also know how to calculate the average acceleration. Okay. So average acceleration is delta v over delta t. So if here we have RF, and then you get VF. We have I, you can get vi. Okay. So when we text vf minus vi, you can get a delta v. Okay, delta v. Yeah. And delta v divided by time interval, you can get average acceleration. Okay. Now we consider instantaneous acceleration. Okay. Yeah, we just take the derivatives of velocity with respect to time. You can guess instantaneous acceleration. Okay. Yeah. Here, just give you some different changes. Okay. That can occur when the particles accelerate in two dimensions. Okay. In the first case, the magnitude of the velocity vectors may change with time as is one-dimensional motion. Okay. Second, the direction of the velocity vectors may change with the time, even if its magnitude remains constant. We change the phase angle. Okay. Or the last case, both magnitude and direction of the velocity vectors may change simultaneously. Okay. So we have many possible cases to make the different acceleration. Okay. Look. We have this trajectory, right? Yeah. And this is the positions. Position. We have vector r, right? Distribution point. We have vector r. So we can guess instantaneous velocities. So instantaneous velocity is tangent line, right? Tangent line of trajectory. Okay, so here you can get the vector r. Here you can get the vector v. Okay. Yeah. Or for example, here we have y, here we have x, and we have vector r like this. Okay. And for example, this is trajectory. And then we get vector v like this. Maybe I use another color. I use this one. Okay. Now we have vector v. Okay. Yeah. Then now I choose xy coordinate like this. This one is x. This one is y. Okay. So we can get this one is vx, and this one is vi, right? So any vector v we can analyze into the combination of vx and vy. So vx is perpendicular to r, right? And vy is in parallel with vector r, right? Okay. Yeah. So I can refer vector v to the reference to the coordinate system like this. Okay. And vector r refer to vector x to another reference coordinate x y. Okay. Yes. So here we have vector r. You can get two components, x and y position, right? X-axis position, y-axis position. This is the values. So we should use the unit vectors I overhead and j overhead. We get vector v with the I, okay, velocity and acceleration. Okay. So if we have three dimension, you get vector r a x I overhead plus y j overhead plus z plus z k overhead. Okay. Yeah. Or as mentioned before, you can use the complex number, right? Complex number. We have magnitude and phase angle, right? So if yeah, of course you can use it r a r s I overhead plus r y j overhead, or we can use magnitude of r with the phase angle, maybe alpha like this. Okay. And similarly, we have with the v a v with the beta, and we have with the a acceleration is magnitude values of I with the phase angle Riemann. Okay, it's up to you. Okay. So if you use this one like holophone, right? Holophone we consider magnitude and phase angle. Okay. For example, look, as a certain instant, the position, the velocity, and the acceleration of a particles like this. Okay. So if we consider this one, this is the format of coordinates, right? Coordinate. We have x-axis, we have y-axis. Okay, so write to r v a in holophone. That's mean magnitude and phase angle. Magnitude, phase angle, magnitude, phase angle. Okay. So now we have three vectors. We have three vectors. R, V, I, okay. So in the same holophone, this is the holophone, right? X1, okay. We say this one is reference axis. This one is reference axis. Okay, so we always stay here, right? So now with the R, with our help. R. How I overhead you can use the units like that. Mine 97 J overhead. Okay, so if we consider this one belong to four parts. Four parts. That's right. Yes. So when R is here. Do you read? Yeah. Okay. So if we follow counterclockwise, you get positive, right? And clockwise, you get negative. Okay, so we get this one is phi r. Right? So if we know this phase angle, you can calculate phi r, right? So phase angle get what? For example, this is I say theta 1. So you get tan theta 1 is absolute. So 1 divided by tau, right? So you get theta 1 is tan to the power of 1, right? 27 over tau. Please. 66. Okay, 66. It is 66 degree. To get over 1 is 6 degrees. Right? Because you here and look. Okay. And then if you stay here and you look with the R, follow clockwise direction, yes, minus.
Right?
Okay. And then if we follow counterclockwise direction, y is 360, right? Minus 66, you get how many? Okay. So that is the reason how reference distance.
Of course,
For the final exam, you can use minus 66.
that's okay.
That's okay.
That's
That's
okay.
okay.
And
I understand.
You stay
Here
here
and then follow
clockwise
direction.
But if you just say
hit the
the
one
166,
0%.
you know?
No?
Of
Of
course,
course, when we calculate hit the one, we base on the absolute values of minus definition one help. This is a final result. Minus 66. Okay? Yes. Okay. And similarly, you can get V.
with the V, we get 21
I overhead plus 19
trace
overhead.
Okay, so that belongs to the first part. The first part, right? So
we can get
how many degrees?
42.
So
you can get 3, 42.
42 be
Here.
you get 50, right? Okay. Yeah. And then we get the I. But the I acceleration is how minus 50 overhead plus overhead with the plus. So this one belongs to the second part. Right? And the face angles is 144. So here. Okay. So now I can indicate the R with the V and the I in the same coordinates. Right? Yes. Think more. Now I have another reference y is the x. Okay. Now we have vector r here. Okay. Yeah. So if we consider this one, we don't know what's the moving direction of the object. We don't know. You just indicate vector r with the v with the I, but we don't know what's in the moving direction. Do you read me? Right? So if we would like to know the moving direction, we need to compare with the R and with the V and with the I, right? So if they have the same directions in racings speed. Do you read me? So if we have different direction in racing speed. Okay. But when we consider this one, we have the same axis, the same direction. We have the same direction. You can compare, you know. Yeah. So now, if the same, we say what? In rees is what? Distance. Right? And here, if different, you say the reasons. Distance. So if we have one dimension, it's very easy. One dimension motion. It's very easy. You can get which case for the racings, which case for the racing speed, blah blah. Now we have two dimensions. Right? Two dimensions. So how can we compare? How can we know if we get increasing distance, decreasing distance, or increasing space or decreasing space? How can we know? How can we compare? Okay. How can we compare? Extra points. 2% extra points. Yeah. Projection. Yeah.
We have two axes. X, Y, and we project motion on the x-axis, y-axis.
Think about projection. This is the theory of linear algebra, right? Linear algebra we talk about projection. Okay. If we know projection, that means we prefer V to R, I to V. Right? You can compare. We can get increasing on it. How can you get projection? So here, look, V is here. Okay. So now, if we would like to get projection, I say this one is vector x. This one is vector y. Right? And then I translate vector V to here, and then you get here Vx. Here is V y. Right? Okay. So or here we say V parallel because Vx is parallel with R, and this one we say V perpendicular. Because Vy is always perpendicular to R. You get projection. Yes. So if V parallels here and with R here, you know the same direction, so we say increasing distance. So if with the V like this, with the V like this, you know, and now you can get here is V parallel, right? And here you can get V perpendicular. You get the decreasing distance. This is projection. Think about linear algebra. Okay. How linear algebra will have to study projection? Yes. Projection. Or maybe it's this afternoon we will study projection. Right? Okay. Do you understand? So now how can you compare A and V? You find projection I into V. Okay. So here you get V, right? So we say this one is this one is Vx. This one is sorry, this one is X. This one is Y, right? Okay. And then you find projection of I into V. Where is I? So I guess I here. So maybe like this. Okay. So now we can get I parallel. I just said parallel. I cannot say it's the same direction or opposite. Just parallel. Okay. And then now you can get here I perpendicular. Right? Now look. Now I is opposite to V. So this one is the decreasing speed. Okay. And we can consider the up to now you get clockwise directions of clockwise direction. Yeah. Understand? So here we just have two directions, clockwise direction or counterclockwise direction or clockwise direction. Okay. So here look. We perpendicular like this direction. That means the object will be following clockwise direction. Okay. And then you need to convert clockwise direction or counterclockwise direction into x-axis or y-axis. Yeah. So now I give you further analysis of increasing or decreasing speed.
Any questions so far? Okay, no questions. Continue. You get extra point 2%. Extra point. So please help Mr. Tong. Okay, you get extra point. Yeah. It's this slides I just explained to you, right? For example, here you get with the R, here you get with the V, right? So you can find the projections of V into with the R. Okay? With the R. So here you can get x-axis, right? It's up to you. You can say x and this y. It's up to you. Okay, this is y-axis. Okay, y-axis. So here you can get V perpendicular, and this one is V parallel. Okay. Yeah. So V parallels is the same direction with R, so you get increasing distance. Okay. And the direction will be follow clockwise directions because V perpendicular here, right? We follow clockwise direction. And similarly, you can find projection of I into V. Okay, here you can get this is X, and this one is Y. Okay. Yeah. So we this is increasing speed, and with V will follow counterclockwise direction. Okay. Yeah. Okay. Or we can say like this. Okay, look. Here is vector R, here is vector V. So we can say V perpendicular mean that the direction change of the position vectors. Right? The position change because the V perpendicular here, so theta will be smaller. After some time, theta will be smaller. Okay, after some time, the R will be here. Right? Okay. And V parallel means the magnitude change of the position vectors. Okay? Yeah. So after some time, vector R should be like this. Should be like this. Why? Because V perpendicular in parallel with R. Okay, the same direction. So after some time, you get more distance. So R should be here. R should, the magnitude of this is RF, this one is RI. Okay? And because the direction change, the direction will follow clockwise direction. So this is theta F, this is theta I, this is theta F. The theta F is less than theta I. You read me? So after some time, delta T, you get here is RF. Here is RF. Okay? Do you understand? How about you? Any questions? Okay. Any questions so far? Okay, good. So this one. So here we have A parallel. A parallel means the magnitude change of the velocity vectors. Okay. So and so can we draw VF? For example, this is VI. So can we draw VF? Yes. Okay. So VF will be like this or like this. Please tell me case 1 or case 2. Case 2, right? Why? Because after sometimes the magnitude of V is increasing, And then, you know, A perpendiculars will follow counterclockwise direction. So after some time, you can get that the VF will be here, not here, you know. Right? So this one is VF. Do you understand?
Yes.
Yes? It's easy, right? Yeah. Okay, so continue. We have some examples. Okay, at certain times, the position, the velocities, the position, velocities, and acceleration of particles are given by R, V, and A. Okay, so at this instant, okay, how is the magnitude of R changing? Hey, why we get answer? Hey, bị lỗi à? Yeah. Yeah, my mistakes made. Yeah, actually, I need to cover. I need to cover this reference answer, but I don't know why. Let me check. Maybe it's wrong. Later on, I will revise. Okay, I will cover references. Okay. So for how is the magnitude of R changing? So we need to compare R and V, right? And V. So is R turning in clockwise direction or counterclockwise direction? And is the speed of a particle increasing or decreasing? And how is V turning? Okay. So you can use the graphical representation, okay, to answer these questions. Okay. So you need to draw vector R here. Just not exactly. Just I just draw approximately. Okay. For example, here is 3, here is 7. So I know R is in the first column, right? Okay, so I just draw with the R. So with the V, we have 4J. Okay, so here is with the V. Okay, it's with the V. So you need to find the projection of V into R. Okay, so here you can get V perpendiculars. Here we have V parallel. Okay, so V parallels is in the same direction with R. So we have the magnitude is increasing. Okay, and then V perpendiculars like this, so that means we follow counterclockwise directions. Okay. Yeah. So after some time, we can get vector R F like this. F like this. Em right, Khoa? Hả? Any suggestion, Khoa? Yeah. Intelligence. Smart students. Okay, so now is this bit of particles increasing or decreasing? We need to compare V and A, right? V and A. So this is vector A, right? This is vector V, this is vector A, right? This is belonging to the fourth column. Okay, so here you get A perpendicular, here you get A parallel. So A parallel is opposite to V, right? So this is the reason. This piece is the reason, right? And then we turn is turning clockwise direction, right? Okay. So after sometimes you get VF like this. VF like this. Okay, the VF. This is the VI, this is VF like this. Yeah. And similarly, here they give us the information of polyphone, right? Complex number. We have R, magnitude, and phase angle magnitude. Yeah, this one for your reference. Okay. Yeah. Any questions so far? Questions? Do you understand? Okay. Yeah. Good. So now we find the acceleration vectors. Okay. Just some basic theory. Okay. So to get vector A, you need to know what is Vi, what is Vf. Okay. So if we know Vi and Vf, you can get A, right? Anyway, if you would like to indicate vector A, you need to know Vi and Vf, right? Vi, Vf. Yeah. Multiple choice questions. Okay, a particle undergoes acceleration with A while moving from point 1 to point 2. From point 1 to point 2. This is acceleration. Sorry, this is velocity, right? This is velocity. Which of the choice shows the velocity vector V2? V2. We need to determine the V2. Is the object moving away from point 2. Okay. So we just think about we have Vf minus Vi, right? Vf minus Vi divided by delta t. Delta t is constant, right? Delta is constant, right? We have vector A is Vf minus Vi divided by delta t. Okay, delta t. Okay. So now they give the information of A and Vi, so you can get Vf, right? Vf. Okay. The answers will be C's, of course. Okay, you just remember the formulas. Okay. All right, you just move with the Vi V1 here, right? And A plus with the V1, with the V1 means with the Vi. Okay. And A is Vf minus Vi, so Vf is A plus Vi. Okay, this is with the I, this is Vi. So you can get A is Vf, right? And Vf is V2. See. Right? Yeah. Good. Okay. Continue. The diagram shows 3 points of a motion diagram of the moving direction. Particle change direction with no change of speed. Okay, the speed constant. This is V1, and this one is V2. You know the magnitude. The magnitude is fixed. Okay, just change the direction. Okay, just change the direction. So this one is X. This one is Y. Okay. So what's the acceleration at point 2? Point 2. Okay. So here is Vf. Here is Vi. Okay. So we have vector I is Vf minus Vi. Okay. So here. So you get vector I like this. Okay. So the question, the answer is B. Actually, it should be like this, right? A little bit. Okay. Yes. Yeah. Okay. right?
Yeah.
Yeah, just
I
I
mean,
mean,
you
you need to
get
get the exact scale, you know. Okay, this one like circular, right? Because the magnitude of velocity is constant, right? So just you know, just skew a little bit, right? Just skew a little bit. Now, session number two. Okay, session two. Two-dimensional motion with constant acceleration. Okay. Yeah. Of course, for constant acceleration, we have five important formulas which are discussed from lecture 2, part 2. But now we just think more dimension, right? We have two dimensions. So we have vector V is Vx and Vy. We have two components. Okay. Yeah. And we have five important formulas, right? The first one here. Vf is Vi plus At. Okay. We analyze into two components. Okay. X-axis and y-axis components. Okay. Just think about for more components. Okay. Very easy. And for example, this one we have If is Ri plus Vit plus half At squared. Okay, and we know we analyze this formula into x-axis components. X-axis components, so we can get this one, right? And for y-axis components, we can get this one. Okay, with just one original formulas, we can analyze into two formulas with x-axis and y-axis component respectively. Okay. Yeah. Okay. Yeah, VF is VI plus IT, right? So VI you can get VXI, VYI, AT you get AX times T and AY times T. You can get VL. Okay. That means we analyze the formulas into two components, x-axis components and y-axis component. Okay. Example. I think you should have 2 to 5 minutes. Try to understand the example for yourself. Okay, now 3 minutes. Okay, so here they give us the information of v, right? So we have vxi is 20's I overhead, right? And we have vyi, the initial position, right? Vyi is minus 15 j overhead. So if here we have x, here we have y. So we have v xi is 20, is it 20? And this is 15. 15 is maybe minus 15 here. So you can get here is vi. Is vi. Okay. We also give us AXI. Okay. So AXI is 4I overhead. And AYI is 0J overhead. Okay, so that means we get AY like this. AI like this. Okay. A with the A like this. Okay. So we can analyze this one to becomes A parallel, and this one is A perpendicular. Okay. So after sometimes we can get vector VF like this. Okay, the VF like this. Because A parallel is in the same direction with VI, so VF should be the magnitude of VF should be increased, but then A perpendicular follow counterclockwise direction, so it's VF. Okay, VF. So that means you get more VFX, right, and less VFY. Okay, so now you can see VFX. How many? VFX you get 20 plus 40 40 we don't know times, but you know this is positive. Okay, this is positive plus 20, so you get more VFs, right? And this is VF, or this is 0, so VFY constant. Okay, so here, yeah, it's VF, correct, right? So if when we apply this formula, you can get Vxi plus Ax. Vxi is 20, is x is 40. You get here is 20 plus 40. This is minus 50. Blah, blah. Anyway, so you can get this one, right? Yeah. This one. So for velocity vectors in red color, right? If we observe the direction, so here is VI, here is VF. So VF, and then if we translate VF to be here, so here is VF. Right? Yeah, VF. You can see. Yeah, and acceleration vectors in the purple. Okay, purple color. Yeah, constant. Yeah, constant. Because we are considering constant acceleration, so acceleration will be constant. Okay. Now question B. Calculate the velocity and the speed of particles at the times of 5 seconds. Okay, so you just get the certain value, right? So if t is 5 seconds, you get here 40 minus 15, blah, blah, blah. You can calculate the phase angles. So the phase angle here is minus 21. This angle here. Minus 21 degree. Okay, right? Yeah. And the magnitude is 43. The magnitude is the square root of Vxf square plus Vyf square. This here you get 40 square. Here you get minus 15 square. You get 43 meters per second. Okay. Then determine the x and y coordinate of the particles at any times t in its position vector at this time. Okay, that means we use another formulas, another equation here. We already know vi, right? Vxi is vyi. We know ix. Okay, because ay is 0. Ay is 0. So we know ix. Ay is 0. So Ri at the beginning, at the beginning Ri is 0. That means the xi is 0 and yi is 0. So you can get If. Okay. Any questions so far? So we finished session 2, and now we stop. Okay. Next week we continue. Remember to do homework and submit. Maybe it's the next 2 weeks. Enjoy your lunch. See you in the afternoon. Okay.